Welcome back, everyone. Hopefully we recharged and we're ready to go. So before the break, we were talking about mechanical energy and kinetic and potential. Let's put it into context, okay? So what we're going to do is we're going to investigate the conservation of mechanical energy. So what we have over here is I have a little skateboarder. All right, there she is, I think. And we have a skate park, and now we need to pay attention to some things that are going to be shown on the screen. On the left-hand side over here, I have a little box that measures the amount of potential and kinetic energy my skateboard is going to have, okay? I'm not overly concerned with the velocity and with that sort of stuff. What I want us to see is how the energy changes as the skateboarder moves along the track. Now, we are doing one where there's no friction. We're deliberately using no friction because at this stage we're going to use a closed system. So we're not allowing any other forces to act on my skateboarder. So let's put the skateboarder onto the track. Oops, maybe onto the track would be a good idea. There he is, or she, and off they go. So now, right now, you're going, that's nice, Tracy, but all they're doing is going up and down, and there's no readings. And because there's no friction, they're just going to keep doing that forever. And got a smile on their face, so they're happy. So let's put this over here. Oopsie, I took it out of, it's not reading anything. There we go. Now I've stopped that. I need to actually put it here. I'm trying to get, there we go. Let's play again. And I'm going to try get it to stop with the reading. There we go. So at that point, right there, it's at a height of 4.31 meters. And they were going at 4.81 meters per second. Now that was going up. If we look at our totals, and they've done the nice adding for us, the kinetic energy was 694.8. The potential is 2,534.1. Now that's quite high, and I know you're going, but why is the potential so much higher than the kinetic? Because of gravity. Okay, remember we're going mass, which is 60 kilograms, times in it by 9.8 and the 4.31. The velocities, 4.81 is not that high. But this is what I want you to see. The total is 3,228. If I move this further up, let's go here. Look how small the kinetics become. But look how small the velocity was. Almost getting to maximum height. So my potential gets very, very big. But my kinetic is very, very small. My total stayed the same. But as it went higher, the potential got big. The velocity got small because it's slowing down. Now let's take this grid and take it all the way down to here. There we go. Oopsie. Look there. Now, I can't get it exactly on 0, but the skateboard is at a height of 0.01 meters. That's 10 centimeters off the ground. Look how high the velocity is. So, as they went down, the velocity increases. As the velocity increased, the kinetic energy also increased, and the potential got smaller. But the total stayed the same, 3,228.9 joules. Okay, so let's see if this works with a different type of track. So this is just a nice YouTube track, right? Let's change the track. So let's put it over here. There we go. And you know what? Let's change the mass of my skateboarder. Let's make it a little bigger. Okay, maybe not that big. 75. Okay, I'm just changing the height. I'm putting a grid on so it's easier for you to see. So let's put my skateboard, must be on the track. So there we go. Let's see what happens. Oh, I need to press play, by the way. There we go. Okay, so it's not getting any readings here. Oh, I think I've got to put it on the dots. There we go. Oh, no. Oh, doesn't like me today. There we go. All right. So, oh, I am almost got it exactly. Now here, we've got a thing called thermal energy. We're not going to worry about the thermal energy, okay? My total energy stays the same, okay? And I'm not sure why I have thermal. It's okay. So, that's just heat energy because they're moving so much. I'm going to take the grid off, it doesn't help. Height, 3,91. Kinetic energy is quite small. Potential energy is quite large. Of course, it's a much heavier object. But as we go down and we stick onto here, the thermal doesn't change. So here we go. Let's go here. There we go. Again, by the time they get to the bottom, potential energy is almost zero because it's almost at the bottom. Kinetic energy is very high because it's moving fast. Here, when I get to this point, okay, yep, there we go. Here, now they're about the same. My total stays the same, but here, it's now at a height above the ground and still moving. And in fact, it's the fact that my skateboarder has a certain amount of mechanical energy at the top of its motion that allows it to keep going. And it'll just keep going forever if we ignore friction, which is quite nice, okay? And we could do all sorts of things with this track. And in fact, this is the concept that's used, part of the physics that's used, when they make roller coasters, okay? So if we go to one that looks like a roller coaster, my worst nightmare, okay, is my skateboarder can keep going because of the conservation of mechanical energy. When I put my skateboarder over here, okay, now it's ready to go, it has a certain amount of potential energy just because it's sitting over here. Okay, it's not going to read it for me because it needs to be moving. But there's a certain amount of potential energy waiting to go. If we've given the skateboarder enough potential energy, so he's high enough, when that converts to kinetic energy as it comes down, there'll be enough kinetic energy to get it around the loop. So let's see. Watch. There we go. And there we go. And we'll stop it when we've got some readings. Total energy, 4,39, 4,000, I'll say this right for you, 4,319,3 joules. It doesn't matter that he went upside down. Makes no difference. What was happening is potential at the top being converted to kinetic at the bottom, then the kinetic, because it's going up, starts to get converted, and as he goes around, he has a certain amount of kinetic energy there. At that point, they haven't stopped. I know there's no readings. He doesn't stop there because he hasn't gone back to the same height. If this was the same height as that, he would stop. because the mechanical energy is the same. But that gives me enough energy for him to go round again and change what he looks like. So let's go here. Let's start him again over there. Watch. Okay, didn't like giving me readings. I think it will this time. There we go. It's very fussy. It only takes readings from that side. But 4,396, if I now move this to over here, look, 4,396. So no matter where I put my little meter, I'm going to get the same value. What are we taking away from this? Mechanical energy, the total of my kinetic plus my total of my potential added together must always stay the same. So, this is what we needed to see. As the skater falls from rest, the potential energy is at a maximum. That's when he's at the top and he's not moving. Falls from rest. Okay, rest means he's not moving. The kinetic energy is 0 because velocity is 0. As he hits the ground, goes past the ground, potential energy is now 0 because there's no height. And kinetic energy is now at a maximum. And in fact, those two values will be exactly the same quantity. They'll be the same value, all right? And often, we make the mistake in the section to go that potential energy at the top equals kinetic energy at the bottom. It is true, but it's not how we write it, because we're taking all of the mechanical energy into consideration. So, let's consider what happens with a pendulum. Here we need to pay very careful attention. Pendulums come up, and we're going to be very, very tempted to use equations of motion with pendulums. But the way a pendulum moves is very important for us. So if I go here, so here's my pendulum. I want you to pay attention to the graph on the left-hand side. This graph is going to show me potential energy and kinetic. Here they use the symbols the other way around to us. So KE is kinetic energy, PE is potential, and E total is like the mechanical, okay? All I want you to see is this. So I'm going to move my pendulum. Oopsie, let's stop it. There we go. Let's take it to 50, okay? Now, if you look at my graphs, at the moment, my pendulum, it's at rest, has lots of potential energy because it's at a certain height above the ground. My total mechanical is there as well. So now watch what happens when it swings. The potential and the kinetic keep changing direction, but does the total change? No. So now I'm going to see if I can get it to stop in the middle. So it's going very slowly. There we go, almost. Close enough. All that potential energy has changed into kinetic. Okay? So we had maximum energy over here. It changes, and now we get 0 potential, maximum kinetic. But what did I want you to see? And we'll do it on slow again. Is that when this changes, this total for potential, the kinetic and the mechanical energy doesn't change. All that's happening is that the kinetic energy and the potential energy are converting one to the other. So potential's becoming kinetic, kinetic's becoming potential. Why did we have to do this? Because when we look at this, it's circular motion. Equations of motion are for linear motion. So you can't use equations. It's not going straight. When do we use the conservation law and calculations. When objects are freely falling, so we drop an object, pendulums, big NB, very, 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 very important, okay? Because they're going to catch you out with this, because they're not going to say to you, use energy principles. They're going to give you a pendulum or a roller coaster, and you must know that you can't use equations of motion, which is what my next option was, roller coasters. Remember, equations used for problems in an isolated system where the motion is not in a straight line. So what are we going to use? Potential energy plus kinetic energy at position A, top, bottom, doesn't matter where it is equal to the potential plus the kinetic at point B. They may be at the top, it may be at the bottom, it doesn't matter, all right? But this is the equation we need to be using for this section. We've done lots of work. It's now time to refresh, to gain some more energy for the next section, so I'll see you in a couple of minutes.